And this is 9-1 alpha lesson. Okay? So again, this is the first time you've seen this. P-value. P-value is a definition you're accounting for. So let's go back to some other definitions you're accounting for. What is the difference between an observation and experiment? Oh, I know that one because I'd rather say that one because some of the other ones are hard. Good job, not you know. You got no lunch. In an observation, the participant chooses the treatment. In an experiment, the treatment is imposed on the participant. What is the definition of R squared? Proportion of Santa, what is the definition of R squared?
Santa's not that smart.
Joey will tell you.
The proportion
Keep going.
of outputs and inputs. I don't know either.
The proportion of change in the output can be attributed to change in the input. Now, the next one we're adding is the p-value. It's important. The p-value is the probability of a test statistic, as or more extreme that you got, given the null or true. You have that, Sam?
I guess so. What do you want for Christmas?
I want you to understand what p-value is.
Yeah, no, that's a little above my my knowledge.
Okay, so
Happy holidays.
thank p-value. You listening? The p-value, you write this down. The p-value is the probability of getting a test statistic, which is what? Test statistic means a z-score or a t-score, as or more extreme that you got by chance alone, given the null or true. You don't know what that means, given the null or true. So that's a different definition you're accounting for. But, you're going to ask you what click. So the p-value, the probability of getting a test statistic, which means a z-score or t-score, as or more extreme. And what you did get by chance alone had the null been true. And then type 1 and type 2 errors we will get to in the beta lesson. So confidence intervals and a significance test. It's like vanilla or chocolate. It's your option. They're not going to contradict each other. So this is just going to complement what we did with confidence interval. It's a little more formal than a confidence interval, but we're going to give you the same conclusion. It's a formal procedure. Okay? And it always is regarding the parameters. We're not interested in a test about the statistic. That would be simple. You know what the statistic is. You gathered that data. This, you saw, I got ahead of myself, in Chapter 8 PDF and put the null and alternate hypotheses on the PDF that was on your template. So the null hypothesis is what we're testing. H sub naught, H sub 0 is the null hypothesis. We're going to test that. Either we confirm that, or we find evidence that the alternate hypothesis is true. One or the other. So here's an example. Somebody claims that they can shoot 80% foul shots, but we think that they're full blown. So we're going to collect some data. Here is where we start. You said you can shoot 80% foul shots. So the no is that the true proportion, right? Don't do this. You don't put a p hat in there, because the p hat is a statistic. That's a sample statistic. We're saying that the true proportion, the parameter is 80%. The alternate hypothesis is you're less than 80% foul shooter. We think you're exaggerating. The alternate could be one-sided or it could be two-sided. Oh, I mean, that was one-sided because that had an inequality symbol in it. This is one side, right? We're not going to test if the person shoots way better than 80% because we thought that they were exaggerating to get to 80%. It's going to be a one-tailed test. We think that they're not an 80% test. We don't believe that they're better than 80%. There's no point in testing that. So this is an example of a one-tailed test. One side. So here's the example. We could do this. We're not doing it. We could say that the alternate is they're better than 80% foul shooting. That'd be kind of silly. So this is what we're testing in the scenario before this, in the slide. That's another way of writing a one-tailed test, a one-sided test, but it doesn't apply in this circumstance. Two-tailed test would look like this, a not equal symbol. Now listen to this. Confidence intervals are always two-sided. Remember how the confidence interval was symmetric in the curve around the center? They are always two-sided. The test could be one-sided or two-sided. So that means this. We told you, like you have it off your decision tree, like you do a confidence interval or a test. If it's two tails, two-sided, it doesn't matter. But if it's one-sided, you want to do the test. Now there's a way to do it with confidence interval, but it's too confusing. Yeah. Maybe after you keep play it, but it's not something you want to do. If you're doing a one-sided test, a one-tailed test, you want to do a test of significance, not a confidence. Right? So here's an example. The mean weight of pineapples was 31 ounces. Now we're going to change the watering system. So how are we going to write the no and alternate? Okay? So you grow pineapples with a farm. And then you invest money. It's going to cost money to change the irrigation system. You want to test next year's pineapple crop. Make sense? And you spent this money on water. The alternate, I'm sorry, the no is mu equals 31. Well, how do we get, ready? What are we trying to do? We're trying to make it go up, yes? We're not trying to bring the water in and make it go down. But look how they worded this. Managers wonder if the change will affect the mean weight of pineapples. Affect it. Two-tailed test. See, if in the question, you got to read this in detail. Managers wonder if this change will increase the mean weight of pineapples. And this would be an inequality symbol. So you got to look for this key word. And the key word would be increase, decrease, change. If the word just says change, that's telling you two-tailed test, which is a not equal to symbol. I mean, personally, when I read this question, I think I would do it as one tail, but that's not the way it was written. Yeah, you have to write the null and alternate before you look at the data. Make sense? It's unethical to do this. It's unethical to write the null after you've seen it. And this would be it is never correct to write a hypothesis based on a statistic. What's going to happen? You get into the AP test, and you will assume you're going to get an inference question. And you know that you have to follow the template, you'll be used to the template, you get nervous, and all of a sudden you get these symbols mixed up. If you write a statistical symbol in there, you're definitely losing credit. It's not right. It's just not. There's no defending. They're trying to make a judgment about the parameter. So back to the foul shooting. So the kid claims they can shoot 80%. So we said, okay, let's take a sample of 50 shots and then make 32 of them, which is 64%. Well, 64 is less than 80, yes? That doesn't mean that maybe they just had a bad stretch. If we want to be able to make a judgment on this data, not just say because it's lower than it. Is this evidence? Okay, this is evidence that you're lower than that, but is it statistically significant? So here they did this simulation in 400 sets. So all these dots represent 50 shots. And then this is the proportion of shots they made out of 50 if they were an 80% foul shooter. So you see how it's centered about 80%. Okay? And it's essentially symmetric. So there's the distribution. But in this simulation, only 3 times did they shoot 64% or less. 1 time 64%, and then we also have to count what's to the left of that. So 3 out of 400 times. Make sense? If they really were an 80% foul shooter, the likelihood that they got 32 out of 50 by chance alone was 3 out of 400. Not good. Not likely. So here's the p-value. Right? So my definition is a little different than what's in green, but it means the same thing. It is the probability of a test statistic, remember this, as extreme, 64% or more extreme. 3 out of 400. The probability of a test statistic as or more extreme by chance alone given the null or true. So the null in this case is they're an 80% foul shooter. The p-value would be 3/400ths. That's the sum of the data that was at the 64% or lower if they really were an 80% foul shooter. Which is less than 1%. There's evidence that this kid's not a 80% foul shooter. There's statistical evidence. How about this one? Calcium. You should get 1,300 milligrams per day for teenagers. The National Institute of Health is concerned that teenagers aren't getting enough calcium. Okay. That's giving you a direction. They're concerned you're not getting enough. They're not concerned that you're not getting 1,300. You might be getting too much. They're concerned they want to test that you're not getting enough. So the alternate is an inequality. So what happened? They had a random sample of 20 teens. Their statistic was 98 milligrams of calcium, which is lower than 1,300. Yes? And the step was 411 milligrams. They already did this for you. The p-value is 14%. So it looks like this. Here's your curve. 0, 1, -1. That's what I'm used to doing. Now, in this case, what did we get? 1,300 was the center. Your test statistic was 1198. This step is 411. Right? Well, we're going to test this. So, here's what we're testing. We got 1198. 1198 is over here. 14% of the area of the curve is there. 1404. So when they did simulations, 14% of the time, if this were true, they got 1198 or less. You need to be able to do this. Like when you're doing these problems, you need to draw a picture so you can conceptualize what you're being asked. So go over here and say, question asked. What would it mean for the null to be true and interpret the p-value? Well, if the null is true, then the parameter is actually 1,300. There's a 14% chance that the mean value is actually 1,300, and we got 1198 by chance alone. The p-value is 14%. The probability of getting a test statistic of 1198 or less by chance alone is 1,300 with true. So, we are moving to the PDF. We're telling you this. The null. P equals or mu equals, whether it's proportion or a mean. The alternate, not equal, greater than or less than. This is a two-tailed test, one-tailed test. Okay, and here's the definition of p-value. The probability that z or t, as a more extreme, by chance alone, given the null is true. Right? So we're going to pause the video and have you go to 4 questions. 1 and 9, 15 and 19. Number 1, the null, ready, is that the true proportion of kids who do their homework is 75%. The alternate is it's less than 75%. You're not ready because it says the teacher, Mr. Tabbitt, believes less than that. So it's a one-tailed test. When you get to the actual AP test, you would write, safest way is to write both. So write it out in symbols and a blurb. This does not have to be a full sentence. That's the best way to do it, okay? So what happened? P hat, the sample proportion was 34 out of 50 kids. If the null were true, 75% of 50 kids would be 37.5. So why is that 34 not equal to 37.5 kids? Is it because the true proportion of kids doing homework is less than 75%? Or is it due to sampling variability? Makes sense? That's what you're asking yourself.
Wait, what is it, 37.5?
Well, that's 75% of 50. Because the null is that 75% of the kids will never do their homework. Yes? So we got less than 75% by 7%, or 3.5 kids. The p-value, they gave it to you, is 0.1265. The probability, if the true mean were 75% of kids doing their homework, the likelihood that our sample would give us 68% or less is about 12.5%. Here, when we get to the other problem, we'll just edit that, same picture, and say, we're saying it's 75%. We got 68%, and that area is 0.1265. Yes? That's how much of the curve here would be shaded. A little more than 12.5%. The likelihood that if legitimate 75% of the kids did their homework, that our sample generated this 68%, just the variability by chance alone is 12.65%. Well, we got to compare that to an alpha level. So in problem, we didn't do this yet, but we can move ahead. It says, I'm sorry, for 15, it says at the alpha equals 5% level, meaning that's the threshold you take before you collect the data. So we say 5% is the cutoff. If we get a p-value less than 5%, we're going to reject the null. If we get a p-value greater than 5%, we are going to this. What is this? Seriously, you know what this is? F2R. F2R. We're going to fail to reject the null. You never accept the null. You either reject it or you fail to reject it. You're covering your backside. Hoping to double negatives. You either reject the null in this case is 75% of the kids doing homework. Our p-value was greater than the alpha level. You have to pick that beforehand. So what happened? 0.1265 is greater than 0.05. So we would fail to reject the null. There's a lack of evidence that the true proportion of kids doing their homework is less than 75%. And then, so what happened? I worked backwards and said, you don't need to do this. Inverse norm. 0.1265 is the area of the curve. What I get a z-score of negative 1.143. That's where the curve get marked up, for 68%. There's a lack of evidence to reject the null. So here's our null. That should say H of 0, H of A. That's your alternate. That's your alpha level. Our p-value is greater than the alpha level. F2R. Well, ready? The hypothesis was less than that. So if we were going the other direction, we would certainly fail to reject. If we did a two-tail test, we found 100% of the kids in their homework, yes? Then we would reject it on the other side. But in this case, with 100%, we're only doing a one-tail test. So the alpha level's over here. 100% we're over here. We're on the same side of that line as the null. Okay? That's beyond where we're over here. So that's that for 9 1 alpha.